I will briefly address some of the topics or some of the points that Jim Riley also talked about. So we talk about the same flow, stratified turbulence, with this kind of special dynamics, with this layer formation, etc. And I will address now 2 points that are the importance and the relevance of divergent rotational modes in stratified turbulence and of passive scalar statistics in stratified turbulence. So we have, in fact, 2 questions then. If you talk about strongly stratified flows, then people will tend to think in terms of horizontal vortices and internal waves. And I am going to talk about the importance of these vertical and wave modes in stratified flows here. And the next question is, what is the form of passive scalar spectra and statistics in stratified turbulent flows? Because of some observation in the atmosphere and the ocean, and we would like to relate what we find in numerical simulations with real observations then. So first we have to talk about the vertical wave mode decomposition. So we apply Helmholtz decomposition on the velocity, and then you obtain a rotational part that's related to, of course, to the horizontal vortices, and the divergent part, and this part would be completely dominating when you have only internal waves. When you talk about vortices, you can make an estimate of the time scale, and here LA is the characteristic length scale, horizontal length scale of the vortices, and the velocity scale, and this time scale is relatively slow. And in the waves, then the time scale is of course given by the internal wave frequency, and that is can estimate as the aspect ratio of the horizontal to vertical length scale and the Bund-Weisser frequency.
Vertical flow, you obtain the poloidal contribution, which is divergence-free. Both contributions are divergence-free because, according to Boston's equation, the velocity, the whole velocity field is divergence-free. If you speak about Helmholtz decomposition, it's only a Helmholtz decomposition restricted to the horizontal flow. So only the first term is divergent. The whole, it's a classical poloidal decomposition.
Let me continue. I will talk about what the importance of these parts in stratified flows, and you will see this a bit different there. Okay, if you talk about waves then, and if you talk about motions with an aspect ratio about order 1, then you see with strong stratification these time scales are short. If you make an ratio of these vertical and wave mode time scale, then you end up, this time scale ratio is given by the vertical Froude number. And of course, a horizontal Froude number is small then, so we would think there's a separation in time scales in strongly stratified flows. And it would mean that these 2 parts, or the vertical and wave modes, that there's only a weak interaction between them. There's a strong decoupling. But in fact, as Jim Riley said, in stratified turbulence, you get this layer formation, and then you end up with a situation that the vertical Froude number is order 1. And then you see that there is in fact not a separation in time scale of the vertical and the wave mode anymore. So what we say now then in stratified turbulent flows, that these parts, in fact, part of the same motion there. So these both parts play an essential role in stratified turbulent flows. And in fact, it's not meaningful to make to distinguish between the rotational parts and the divergent parts. Furthermore, what this suggests then, with this stratified with Froude number order 1, that it shouldn't matter so much if you do numerical simulations, if you force in the rotational modes or the divergent modes. You should end up with more or less the same dynamics. And that is some thing that I would like to address now. So we did some numerical simulations, just homogeneous turbulence with a strong uniform stratification. In this case, we use hyperviscosity, pseudospectral, and we had rather flat boxes then, because they have a very strong stratification then. And these are the typical resolutions, but we have also varied in resolution, foot number, etc. So the results are quite robust. And then furthermore, we applied large scale forcing of the rotational modes or the divergent modes. Here are some snapshots in a vertical plane of the horizontal velocities. In the top one, you see when the rotational modes are forced. So in this case, we have only we force only in the horizontal direction, not in the vertical direction. And then naturally, you see this layer development in this case. And then at the last scales, you see that vertical foot numbers are about order 1. Then we have here some two calculations with forcing in the divergent modes. We force in a certain horizontal wave number range, but we have to choose a vertical horizontal wave number range, but we have to choose a vertical wave number that we have to force. In this case, we have force in the vertical wave number 1, in this case 5. And then you get a different thickness of the layers then, of course. And in fact, you can say that here in this case is a bit of a mismatch between what you this layer formation that you naturally have. And, you have this vertical foot number order 1, and what you enforce with this enforce then. And then you get a little bit different dynamics, and the calculations are not completely stationary. But in this case, you can already see that the thickness of a layer is quite similar as in the top one. And this suggests that here the vertical foot number is order 1. And indeed, you will see later that the dynamics and the spectra are very similar between this calculation and that calculation. So here the compensated horizontal spectra, in this case forcing in a rotation mode. So we multiplied the spectra with k to the power 5/3. And here are the kinetic and potential energy. And again, you see you get a nice inertial range with a k to the minus 5/3 spectrum in the horizontal direction. And that potential and kinetic fall on top of each other with a constant about a half. Furthermore, if you look at the blue and the red line, so these are the divergent part and the rotational part of the energy spectrum, that they are both here, of course, at the forcing, then the rotation part, of course, is dominating, but in the inertial range, that they are both important, the rotational part and the divergent part. And what's more, in fact, that you have an equal partition between the divergent and rotational mode here in stratified flow turbulence. So we expected that both were important, but it was a bit of a surprise to see that there is about an equal partition between these two modes there. Now in next case, this case we have forcing in the divergent modes. So this is forcing when you have in the vertical wave numbers 1. So you have this rather thick layers then, and there was a bit of a mismatch, and you can see the spectrum. It's not the same as in the previous calculation. So the level is higher, and there's not an equal partition between the divergent and the rotational part. But when you have forcing here in the vertical wave number is 5, then you see you get nicely the same spectra as in the previous case. So again, this constant about a half when you talk about potential kinetic energy dissipation. And again, in the inertial range, you get an equal partition between the divergent and rotational part. So this shows you that you get very similar dynamics and spectra when you either when you force in divergent modes or in rotation modes. It doesn't matter so much, in fact. Then, of course, we said that well, you see that divergent part is still important. So, are you sure that there are no internal waves here in these calculations? So, to look at it a bit more carefully, what we did is we took out certain modes there. We call a time series of that mode, and then calculate the frequency spectra of that mode. And then, if you scale then the frequency with the internal wave frequency, if you have the internal waves, you should see a peak here at 1. Indeed, here, this is for a last scale, so this is for horizontal wave number is 1, and then vertical wave number is 4. So this is a large scale motion, then indeed you see a peak here. So clearly you have internal waves here. Of course you have also then rotational motions here, but here you see clearly a peak. So you have internal waves at the last scales in these calculations. You see also that both the level of this power spectrum is the same for the divergent part and the buoyant part there. Not a sign that you have internal waves there. But what happens then if you go to smaller scales? So again, we have pick out certain modes, calculate the frequency spectra, and that is for horizontal wave numbers 20, and but then for different ratios for the vertical to horizontal wave number. And when you look at aspect ratio about 1, you still see a bit of a peak, but not as clear anymore here at the small scales. So this is a bit dubious if you have then internal waves here. But when you look at more thinner structures, more the elongated structures at the smaller scales, you see there's no peak anymore. So it clearly suggests you don't have anything like internal waves motion anymore at these small scales. And this is even more clearly here for this horizontal wave number is 20, and then vertical is 1/5 of the horizontal one. And if you calculate the divergent frequency spectrum of the divergent modes and the rotation modes, falling over top of each other, and they're just flat, and there's no peak anymore. So clearly, if you talk about then the inertial range or stratified flows, there are no internal waves there. Then related to what we observed in the atmosphere, Erik Limburg has already shown from atmospheric observation that you have quite similar results, that the divergent and the rotation modes play both an important role in the stratosphere in the mesoscale range. Here I show you some observations in the ocean. So these were measurements with a 3 points probe there, and by that you can calculate a kind of circulation, so there's a kind of average vertical vorticity and a horizontal divergence. And Peter Muller did it on different scales, from scales about from 10 meters up to kilometer, 2 kilometers. And then you see that here, vertical vorticity and horizontal divergence, that are both of the same order there. It's quite similar to what we observed then in our calculations there. So this makes a bit of a suggestion that, in fact, on these scales, on this mesoscale range in the ocean, perhaps you have this something like stratified turbulence there. So if you measure this kind of divergent mode, it doesn't mean that you have internal waves there directly. It can be something else. The next point I would like to address, I have some time for that. It's very short then. The classical oblique of Corsin theory for pesoscalar in locally isotopic turbulence is this one. So you have this minus 5/3 energy scalar variance spectra, and for the second order structure functions, then you get this r to the power 2/3. So this classical stuff for the isotopic turbulence then. Then related to what we see in the atmosphere. So this is in measurements of the spectrum, horizontal spectrum in the middle or in the troposphere. And what you observe there is from scales about 500 kilometers down to about a kilometer. Then you see a minus 5/3 spectrum in the pesoscale. I think this is ozone or something like that. And if you calculate the second order structure function, it is in the lower stratosphere, in the same mesoscale range, or about a kilometer up to 500 kilometers, we see about this r to the power 2/3. So this is similar to what you observe, similar to consistent with our book of Corsin theory. But this is rather remarkable because it's a mesoscale range and it is strongly anisotropic here. So this is clearly influenced by stratification there. And these scales are far from isotropic there. Okay. So you can't explain this by mixing isotopic turbulence there. So people have tried to explain it by, well, perhaps it's mixing by internal waves or by two-dimensional turbulence there. But we would like to see if we can observe the same in our calculation of stratified turbulent flows. So again, we did similar kind of calculation there. So uniform stratification, forcing at the large scales, hyperviscosity. And in this case, we have applied a horizontal mean Pascal gradient, not a vertical one, because then you would expect completely the same statistics as for an active scalar. And then we know already that we have a -5 Hertz spectrum. So we look at the less trivial case as a horizontal gradient in this case. So here are the compensated horizontal spectra then, again for the turbulent kinetic energy, potential energy, you get again inertial range, what we would expect, at about a half there with a constant half. But I show you also then the compensated spectrum for the scalar variance. And here indeed you see that again you get an inertial range, you have -5 Hertz spectrum here. What's more in fact that in this compensated form, the spectrum falls on the spectrum from the potential energy and the kinetic energy. It was a bit of a surprise there. Then briefly, if you look at the second order structure functions, then again we get a nice inertial range with r to the power 2/3. So that is very consistent with the book of cosine theory there. So I come to the conclusion then. So if you talk about inertial range dynamics and mixing of stratified turbulence, we have equipotation between the divergent and rotational modes there in stratified flows. And the dynamics of rotation divergent modes appear to develop on the same time scale. So not really a separation between divergent and rotational modes there in this flow. Furthermore, we calculate the scalar variance spectra, and then we observe in horizontal direction -5 Hertz spectrum. And the cons is about a half. And again, this is very similar to what you observe in isotopic turbulence. So, well, there's a bit of a question mark. We don't know why that is, but that is what we observe here. But this, what we observe in numeric simulations, is quite similar what you observe in atmosphere and ocean for the Pascal and the divergent rotation modes. And if you want to have more details, you can find them in these two references there. So.
I'm not sure I understood the argument. Why would atmospheric 5/3 for cohesive scalar couldn't be explained just with two-dimensional 5/3 turbulence?
Can be but there's an alternative explanation there. But at least it's not isotopic turbulence that is causing this spectrum.
Two-dimensional isotopic turbulence. No third dimension.
Yeah, okay, that can be another explanation, but the question is, do we have two-dimensional turbulence on this scale, on main scale range? There are some other observations that contradict that.
You do have two-dimensional spectrum of velocity, which is 5/3. No
Yeah.
matter what else.
Yeah.
It will give you passive scalar 5/3 horizontal.
Yes. Okay.
No matter what.
Okay, but there's some observation that suggests there's no inverse energy cascade in this range.
You've been here on the first day?
Yeah. Well. Okay.
But to further clarify this, maybe it was worthwhile to look into the intermittency corrections to this. I mean, Luca Vivarala had introduced this local, has shown these local scaling exponents, and you could do the same, really focusing whether there are intermittency corrections which would favor this three-dimensional view, or whether there are none which would favor the two-dimensional.
Yeah, but indeed, I didn't show you, but I've also calculated for the fourth order structure function, and then you see that clearly there's a trend of increasing intermittency at smaller scales. So that is present in these calculations. But it is even more extreme in you look at the stratosphere. Then you have a very sharp increase, I think, of the intermittency, and that is not something we observe in the calculations. So extreme.
I just want to defend the two-time scale analysis a bit. I think anybody who's ever used it on this problem understands that there is a problem with it, and that the dispersion relation goes from n, which is a big number, to 0, which is a small number, and that's the basis of the time scale separation. But to defend the analysis of it, that tells you exactly where to expect the nonlinear interactions, because you don't have these resonance considerations that are turning them off. And those where you so that analysis is useful, and it tells you where to expect the interactions, and that's precisely where you saw them.
Okay, yeah.
On this issue of the range of wave timescales and the issue of wave vortex coupling in general, there's been some recent work in the stratified rotating community, which is summarized in a little review on my webpage if anyone's interested. The point being that as the Rossby number gets big, one comes toward this kind of problem, and there's a very clear case of a non-resonant but highly significant wave vortex coupling that's recently been discovered. I'll put the details on the book blackboard. Any more questions? Okay. Yes.
In the past simulation, where is your on scale?
In fact, we don't resolve the osmometer with this hyperviscosity calculations.
Okay, on wave number.
So that is really at the large wave numbers. So we only look at scales larger than the osmometer of length scale then.
One more other question. In the wave number for the K vertical axis,
Yeah.
you don't have a distinguish between vortex mode and wave.
What do you mean?
All have zero wave, zero frequency. Mode on the K vertical.
I don't know, but okay. But when we force in rotation modes, we don't have any variation in the vertical. So we don't impose a length scale in a vertical. When we just we have just forcing in the vertical modes there. So we don't impose a vertical length scale there. But we impose a vertical length scale when we have forcing in the divergent modes.
Okay, maybe we